Welcome back. Let's go through the lecture notes, the algorithm analysis section. So you might want to make sure you have these notes. Maybe you'll want to print them out and follow along, or whatever works best for you. But I'm just going to go through these and talk about these. So we talked about why to analyze algorithms and a little bit of math background in the previous video. You should go watch that. But here we've got some graphs of common time complexities, the ones we're going to deal with in this course, going from good down in here to bad up in here. So once again, briefly stated, time complexity is trying to describe the relationship between the size of a problem and the execution time. That is, how much longer does something take to execute as the amount of data increases. So N means that as the data size increases, the time to execute increases proportionally. Okay, and now you can do worse than that, or rather worse than that up here. These are all worse than that, and you can do better than proportional down in here. There's these different formulas in here. Okay, so this one here, for example, is really bad. It's saying that as the problem gets bigger on the x-axis here, the time just takes off. So a little bit of data, it'll finish not too long, but start adding some data, it takes a crazy amount of time to finish. And this one here is saying that, like, you have some data, it'll finish in say this long, but you could add a whole lot more data and it'll take longer, but not a lot longer. Okay, so this is good. It's hard to do better than this log n thing, and this is very, very bad up in here, n to the n. All right, how do we determine these? Well, we have a couple different methods. Basically, we have three methods that we're going to look at. We have a test, which I like to call empirical, or maybe the other way around. We can just measure stuff, or we can do some what I call rules of thumb kind of analysis, or we can do math analysis. So it turns out that well, there's pros and cons to all of these. So math is usually too hard. Now I'll show you a math analysis for bubble sort, which we can kind of do. But bubble sort's a pretty simple algorithm. Usually for real life algorithms that you're going to write, the math is just too difficult. We can also do an empirical test. That was, we can just use a stopwatch or a counter, right? So we stopwatch, or a counter, and that works. Or we could do these rules of thumb analysis, which we're going to go through, right? So let's do this test, empirical test, for a classical algorithm called a fractal dragon. All right, so I'm going to pull this up on my monitor and go through this. Well, before I pull it up on the monitor, let me just explain the algorithm. So it's called fractal dragon. So the basic idea is you take 2 points, and what you do is you find the midpoint, and then you offset by that distance. So basically, given points 1 and 2, you find point 3. And then you connect the dots. This is like level 1. Okay, then you repeat that. So now we have this line segment, the 1, 3 line segment. You do that again. So you find the midpoint between 1 and 3, and then you offset it. So you get that. And then you do the same with the 2, 3 line segment. You find the midpoint and then offset it. So you get this. This is level 2. And you continue like that. So there'd be level 3. So you take this line segment and do the offset thing, you get that. And you take this line segment and you get that. And you take this line segment and you get, oh, what is it going to be? I think it's going to be that, right? And then you get this one, this will be that. I might have messed up, but that's pretty close. So you're taking a segment a line segment and continually subdividing it. All right, so there's basically, there's 3 lines here. There's 1, 2, 3, 4 lines here. There's 1, 2, 3, 4, 5, 6, 7, 8 lines here. Actually 2 lines. There's 8 lines here. If you did it again, there's going to be 16 lines. Okay, so you might have a clue on what this is doing here. If you have say n is the size of the problem and the big O of n. So in this case, big O of n is the work being done. It's the time or the work, you know. It's how it's associated with how long the algorithm takes to execute. Okay, but sometimes we use actual time. Sometimes we use something called work. Here we're using work, and the work is the number of lines that are being drawn, number of lines. And n is the, it's a little hard to, it's the size of the problem. We have to get into a little more detail, but if you look here, there's for level 1, level 2, level 3, and level 4, you're going to have 2 lines, 4 lines, 8 lines, 16 lines. So for level 5, I'm going to have 32 lines. If you graph this, it's going to look like this. It's going to be 2 to the n. Okay, so this was a certain kind of big O analysis. It wasn't rules of thumb. It was kind of a graphical, thinking it through kind of analysis. Sometimes you can do that, but we're not gonna do that all the time. But sometimes this works. And let me show you this using an empirical method, a measurement method. All right. Okay, so I've got my monitor up, and I've got this little demo program that's posted on the website, and you can pull this up if you want. And then I made a little Excel chart of the size of the problem, or the level, and the time that it takes to execute. These are all zeros right now, but let's execute this with level 0, and we get that. I was calling that level 1, but it's same idea. I was calling that level 1 in the previous thing, but this program is using level 0 for that. If we start the next level up, okay, that's one, making the problem 1 more bigger. Okay, it's level 1. And let's go 1 more bigger than that. Notice how for these small numbers, these small problem sizes, it executes pretty much instantly. So that's what I was saying earlier about, for small data sets, it doesn't matter what you do. With modern computers, they're going to get done pretty quick. Okay, but as the size of the problem continues to grow, all right, now we're up to 8. Now it's starting to slow down. I have a pretty fast machine, but it's starting to take some time. Okay, now it's human time, human level time. That is, times humans start to worry about. It looked like about half a second to me, maybe 1 second. Let's do 11. So let's call that 1 second. All right. So I'm just going to put in 1 over here on the time. Okay. And let's do 12. Look like I'm going to call that 2 seconds. If we had a stopwatch, we could be a little bit more accurate. Or you could put a software timer in the code, right? Okay. 2, 1,000, 3, 1,004. That looks about 4 seconds. I'm just kind of counting the seconds out. What are we at? What are we at now? 14? 1, 1,000, 2, 1,000, 3, 1,004, 1,005, 1,006, 1,007. It was maybe, I got to 6. You know what, I'm going to round it to 8 because, okay, 6, good enough. I wanted it to be 8. The other one might have been closer. This might have been closer to 3, right? I mean, you know, I'm just rough measuring this, not real accurate. 2, 3, 4. I got to about 12 seconds. That felt like about 12 seconds to me. I might be able to pull a timer up. Oh, here. Yeah, we could use that, huh? Oh, but it won't stay. Well, anyway, whatever. You get the idea. Move that back. Let's do 16 now. I counted about 35 seconds. I might have been going a little bit fast. Let's call it 30. Now, if we did it again, it's going to take close to a minute, approximately. Once again, these are very rough measurements because I'm not using an actual stopwatch. You could get more accurate, but it's going to be about 60 seconds. You could try this at home if you're not believing it. Okay, so that's a 2 to the n shape. The curve of this is 2 to the n. And it's growing pretty quick. Like, it's going to get into days and weeks pretty quick. Like, this next one's going to be, well, this is 2 minutes, basically. This is 4 minutes. This is 5 minutes. So we're going to be to 10 minutes, 20 minutes, 40 minutes, then about an hour. More than an hour, but let's round it to an hour. Then 2 hours, 4 hours, 8 hours, 16 hours, 32. So a day, right? We're at a day pretty quick. Then, 2 days, 4 days, 8 days, 16 days, a month, right? So by the time we get to about 30, we're at a month. And then we're very quickly into years, centuries. How big is 34 for a computer? It's like nothing, right? So if you went up to, like that many, what's that going to be? It's going to be eons. It's going to be more time than the universe has existed. All right. So this grows incredibly fast. Let's go ahead and say put in 40. All right, I'm just going to let this run over here. Maybe we'll come back if I remember. You can try this at home. This file is posted. You can run it. All right. I'm going to go back to the note. So that was Towers or Fractal Dragon. There's also Towers of Hanoi, which is also a 2 to the n algorithm. And the code, the demo program for Towers of Hanoi is posted. You can download that and run it if you want. Anyway, both of these algorithms are 2 to the n. They're just about intractable for n of anything bigger than 10, 20. We call that intractable because it's going to take so much time that no one's willing to wait for that. All right, so that was empirical measurement. That was just using a timer, or you could also use a counter. You could use a software timer or an integer counter or a manual stopwatch. You just measure the execution time for various n's and you plot that. And we got a 2 to the n. So there's good and there's bad about that. The good thing about that is that for complicated code, well, there's often no other way to do it other than an empirical measurement. The analysis is just too complicated. Okay, the bad thing about that is that some algorithms, have a very bad time complexity, and just waiting for the thing to execute you know, maybe a problem. Like, the good thing is you can execute it for small n's and get the shape of the curve, and then you can extrapolate what it would be for big N. But if you really wanted to prove that it takes a long time for large N, the problem with that is you'd actually have to wait for the thing. Okay, well, so empirical is good and it's bad, but often it's the most practical thing to do. I use it a lot. Like when I write an algorithm, often the easiest, sorry about the little noise there. When I write an algorithm, often the easiest thing to do is use an empirical method. That is, put a counter in there or put a software timer and actually generate some points and then plot them and get a shape of the curve. Let me turn the camera back on here. So back to the notes. Yeah, it didn't really nothing's showing up on the screen, but it is running. It's just way in there inside the depth of recursion in there. Well, anyway, okay, so another thing we can do besides empirical is we can do this rules of thumb, or also called running time analysis, right? So here's a couple of examples. So this one is big O of n. It's just a simple loop, right? And this one is big O of n squared. It's a nested loop. So often, but not always, when you see a single loop, it's often big O of n, but not always. You really need to look. And n squared is often a nested loop, single nest, two loops, nested, one loop nested inside of each other, two loops nested. Okay, but not always. And you have to look at what's actually happening here. So for this one here, we've got this initialization code. That only occurs once, so we ignore that. It's just a one line of code. Doesn't matter how big n is. In this case, n is the 3 here. So it doesn't matter how big this n is. This line of code here is not going to take any longer or shorter because of n. So we just ignore these kinds of initialization lines, these lines that only run once, just ignore them. And then look at the loop, and then look inside the loop and see if that has what we call a constant time. That is, does this box right here, the target of the for loop, does it have what we call a constant time? And it does. Now, a constant time is a time that doesn't vary dependent on n, right? And n is this 3, and it's not in here anywhere, so it doesn't matter. If that bothers you, let's see, we could make this n, and then we could say over here n equals 3. I guess int n equals 3. Okay, so there's no n in this inner loop here, so that's constant time. So we say this is big O of 1, or constant time, and that this summing statement is the target of the loop, and it has a time complexity of 1. Then you look at the loop, and what's the time complexity of the loop itself? It's n, because it's counting from 1 to n. So that's big O of n so we have the whole thing together is big O of n, because we have a constant time thing inside of a loop. Okay, so likewise, let's do this one. So this one here is not dependent on n, this inner target, so that's big O of 1. Okay, the outer loop, well, let's start at the top level loop. That's going from 0 to n. So the outer loop is executing n times. So that's going to be big O of n. Okay, the inner loop is going from 0 to n as well. Okay, so that's also big O of n. So then you sort of parse it from the inside out. So that means this thing together is big O of n. And then the whole thing is a big O of n inside of a big O of n, so it's big O of n squared. Okay, so those are our running time analysis rules of thumb that we're going to use. So summary, you ignore the simple constant time big O of lines such as this initialization. or lines that might execute only once. You look at any tests. Oh, we don't have any tests in here. We don't have any if-thens or switches. So, well, there is a test in the for loop. There's I less than n. That's not dependent on n. You know, this little execution. It takes the same amount of time to do this, just this part. So that's a constant time thing. But in some cases it isn't. I mean, you have to look pretty carefully. Like there could have been, for the conditional in here in C, you could write a thing that walks through all n to make a decision. Then that would be BigO of n. Okay, so you got to be careful. You got to look at these more carefully. All right, now we're gonna do more of these, and a lot of this is just by watching, you know, your instructor run these, and that's kind of how you learn. You sort of get a feel for how to do these things right here. There's a lot of hand waving, and it takes practice and experience, right? So my goal for this class is just to provide an introduction for, you know, exposure to you, first time exposure to this material. It takes some years for this to kind of soak in. So this is a first semester data structures class. You get some exposure, let it soak in for a couple of years. You'll take more data structures classes if you continue on in computer science education. There's usually some at the junior level, and then you might have opportunity to take an elective at the senior level. And then if you go to graduate school, you'll take more and more and more and more and more. All right, so we'll do some more of these. Okay, there's also, yeah, let's just do some more of these. Okay, there's one more, another thing that happens, and that's recursion. Now we need a whole section on to talk about recursion. We're going to look at that later. We have a whole set of techniques for doing recursion. But sometimes recursion is really just a loop. And we looked at this previous single loop, and it was BigO of n. This one happens to also be BigO of n. Now, why is that? Well, you know, I mean, if you look at a loop, you start out at n, and or rather, you start out at 1, and you increment up to n, so it goes n times. Here we're starting out at n, we're decrementing, and then when it gets to 0, we stop. So it's very much like a loop, and this turns out to be BigO of n. Okay, this is a little tricky to see. We'll look at some more, but when the recursions get more complicated than this, we can't just even do what we just sort of hand waving did just then. We have to have some more techniques, so we'll look at all of that. Okay, so what I'd like to do now is just go through some different algorithms and apply these rules of thumb, hand waving rules that we used over here. Okay, let's go through that. So there's something called the maximum subsequence sum. This is just a classical data structures problem. Here it is for one example of that problem. So given a sequence of positive and negative numbers, there is a subsequence, a contiguous subsequence that has the maximum sum. Right? So here's just a list of numbers: 7, a -9, a 2, -1, 5, 5, -6, 4, 1, and the solution is in yellow. So this yellow area is the maximum, the biggest contiguous area that has the maximum sum. That's right. So and how do you do it? Well, you just do it like humans do lots of things. You just sort of look at it and scratch your head and kind of think a little bit, and very vaguely sort of like figure stuff out like humans do. Now we need, to make a computer do it, we need to be a lot more precise than that. But honestly, that's kind of how we did it, right? So like these 5s look good. Let's start there. So you grab those 5s, I got 10. So if I try and go to the left, -1, if I add that would make it smaller. But then I could get the 2. So that would counteract getting smaller from the 1, right? So start with 5 and go this way and get smaller, and then go that way and gets bigger, and I'm still good. But if I try that again, like if I get the 9, I'm 9 less. That's bad. But if I kept going, I'd get 7 more. Well, 7 doesn't make up for the 9, so just stop here. And likewise, let's try and go to this way on the 5. Like if I go this way and add the 6 in there, or subtract the 6, I'm getting smaller. What if I grab the 4? It's still smaller. I'm still down by 2. And if I grab the 1, I'm still down by 1. So just leave those guys out. Okay, so that's the answer. You could kind of go over here and see if could you get any better, and you can't. Like if you get a 7, then what is the answer down in here? It's 10, 11, right? It's 11. Can I do better than 11? No. I mean, if I grab the 7 and I have 7, which isn't better than 11. If I grab the -9, I've got -2, and now I've got 0. You know, that's not any better. Oh yeah, I could add. No, can't. Well, okay, so anyway, that's the answer. Okay, now let's look at 3 different solutions to this same problem that all have different time complexities. Okay, now let's use the right level of abstraction here, right? So, I mean, we want to look kind of high level. You don't need to look at every single line here. We just kind of need to look at, you know, the right level of abstraction here. See my hands waving around? That's what we call hand waving. So the disembodied hands waving around. All right. So just look at it at kind of a high level. So here's the algorithm. What's this? Let's go through all these lines. What's this line? It's just an initialization. It doesn't matter how big n is. This will take the same amount of time, so just ignore it. Okay, this one is another initialization. You can ignore that. Okay, then we've got a loop. And inside that loop, we've got a loop. Okay, and then we've got the target of this loop here. We've got this. So let's start inside here. So this thing here is just a one-time initialization. Well, it happens every time this inner loop executes, but it's constant time. This line right here doesn't take any longer if n is different. This is independent of n. Okay, so we can ignore this guy right here, this line. Just ignore it. This guy here, this is constant time, because there's no n in there. It looks like, I'm not sure exactly what are we doing. We're taking some element, adding it to the sum, but there's no n in here. So let's call this big O of n 1, big O of 1, or constant time. Let's look at this thing here. So this thing here is big O of 1. This line is constant time. Then I've got an if. This thing doesn't have n in it, so it's constant time. This whole block right here is big O of 1. You could just basically ignore it like you're ignoring this thing up here, and just kind of concentrate on here. So now here we've got k going from I to j, so we got to back out a little bit and see what the i's and j's are doing. So what is I doing? I is going from 0 to n. So this is going n times. Okay, what about this guy? This j. J is going from not 0, but from I to n. So here's where we got to make a simplifying assumption, or we can't do it. Like, if j were 0, this would be big O of n. If j were going from 0, right? If we're going from 0 to n every time, it would be big O of n. But it's not going from 0, it's going from I. So like the first time this loop executes, it goes from 0 to n. Then I increments to 1, and this loop here goes from 1 to n. Then I increments, and this guy goes from 2 to n. So every time this j loop executes, it executes a little bit less. So that's a complexity that just makes it difficult. So we'll round it to the worst case. Okay, so we're going to say worst case big O of n. That's worst case is when I is 0. Okay, so a lot of times it's better than that, but we'll just say worst case. Okay, likewise, we go to this next loop here. We've got this guy going from k equals I, which is the first time through is 0, to j. the first time through is 0. So the first time through it's going 0 times. Second time through it's going 1 to, well, 1 to 0, 1 to 1. Okay, then what? 1 to, so it's hard to say, but it's hard to just articulate, but it's getting bigger. Starts out in the little bit small, and it starts to get bigger and bigger and bigger. As I and j grow, this guy gets bigger. So once again, we're doing this hand waving stuff, and we're just going to say that it's worst case big O of n. So what do we got? We've got this block right here, which is a constant time thing executing big O times. So this whole thing is n. And then we've got a block of stuff around that, which is n times n, so it's n squared. And then we've got a block of this stuff around that, which is n squared times n, so it's n cubed. Okay, so it's an n cubed algorithm, worst case approximation, which is the best we can do with this hand waving kind of a deal. And it's good enough, because we're concerned with large n, okay? And if you imagine n being a very big number, the curve will, for very large n, it'll be very much like an actual n cubed curve. Now we're gonna talk about that more, but okay, this is one example of the hand waving analysis. Okay, that was solution 1 for this maximum subsequent sum problem. So there's a better solution than this. Turns out there's an n squared solution to this. It'll solve the same problem, but it'll solve it faster. So once again, the analysis is similar. Right here we have a constant time operation. Those are inside of a loop, which is approximately n. And then this guy out here is n. So these two end up being n squared. So nested loop, where the outer one goes exactly n times. The inner one goes less than n times, but coming closer and closer to n times as I grows. So we'll just call it n worse. So n inside of n is n squared, right? There's an even better one than that somebody figured out. Somebody figured out how to do this in n time. Okay, so all of this junk in here is, we can just call this big O of 1. Because this is big O of 1, this line, it's not dependent on 1. This line right here is not dependent on n. Sorry, I misspoke. This line's not dependent on n, this line's not dependent on n. Okay, which one executes? Well, they're both the same, big O of 1, so it doesn't matter. If one were worse than the other, you'd pick that. Like if this line right here had a higher time complexity than this one, you would pick the worst one. But these are both the same. So you just assume that this if clause, that the worst case target executes. So this is 1. The if itself is constant time because there's no n in there. That is this comparison that's happening here. And this comparison, they are not dependent on n. So this whole block is not dependent on n. Likewise, this guy here is big O of 1. So, you might want to add these. You might be tempted to add them and get big O of 2. We don't do that. We just deal with 1, some amount of constant time. That's another kind of a hand waving approximation that we do. Okay, all of this stuff here is n, or 1 rather. All of this stuff is 1. 1, big O of 1. Okay, it's the target of this for loop. All of this junk, big O of 1 junk, is in a target of the for loop. So together, it's n. Right? That's the hand waving kind of thing. We're going to do this all semester. What are we going to do? We're going to look at data. We're going to look at the algorithms that operate on that data. then we'll do some kind of analysis to come up with a BigO. And in the process of that, you'll get a feel for how BigO analysis works, and you'll be exposed to lots of different kinds of algorithms. Okay? And that's our goal. You know, that's good enough for a first semester programming class, or first semester data structures class. Alrighty, there's one more algorithm solution to the same problem that happens to have this time complexity, n log n time complexity. But you could look at the chart. Where is that? Whatever. It's worse than some, better than others. Okay, this guy is recursive. Look, there's the name of the. This is a helper function, max3, that does some stuff. But then here's maximum subsequence sum, max subsum, the function name. Go in here. Here it is again, max subsum. So this function is calling itself twice. So that's how you know it's recursive. What else? You could start looking for n's in there. So n is kind of hidden because you're given this left and right integers. You're giving the size of the array, and then it's calculating the size of the problem kind of in here. I don't see any other. Yeah, so there's some lefts and rights going on. It's not easy. The rules of thumb that we've been applying about loops, nested loops, what can you count as constant, that kind of thing, they don't really work here. And we have a whole section of the notes on how to do these kinds of things. But roughly stated, when you have a recursive function, this one is calling itself twice. It could either be real good or it could be real bad. I mean, there's a chance that it could be n log n. There's a chance that it could be 2 to the n. And that's the highest probability that that's what this is, but we really don't know until we learn some more powerful techniques. Okay, so we're going to do that in another section. I think that's it. All right? How do you think fractals is going? Let's check. It hasn't moved at all. I would expect to see at least a dot on there. Well, anyway, you guys could download these EXEs and run them on your home computer. They are safe, although Windows will nag the heck out of you that you downloaded an EXE from the internet and it's going to destroy your computer. But trust me, it won't. I wrote these. I wouldn't do bad. I wouldn't post malicious code. It's not nice. All right. See you next time.